Students, welcome to Sunil's tutorial. I'm Sunil Nirvani and today we'll be doing this chapter called as ionic. Let's see classical definition or the old definition of acid. How do you define an acid? Right? Now, as per the classical definition, acid is defined as a substance. Acid is defined as a substance whose aqueous solution has sour taste. Second, neutralizes a base. Next, turns blue litmus red. Turns phenolphthalein colorless. Turns methyl orange pink. And reacts with metals to give hydrogen gas. Reacts with metals to give hydrogen gas. Right? That was the classical definition of acid. So it says that any substance that can turn, any substance whose aqueous solution can have a sour taste, neutralizes a base, turns litmus paper red, phenolphthalein colorless, methyl orange pink, and reacts with metal to give hydrogen, is an acid. Next, let's see classical definition of base. How do I define a base? A base is defined as a substance whose aqueous solution first has bitter taste, right? Neutralizes an acid. Next, turns red litmus blue. Turns phenolphthalein pink. Turns methyl orange yellow. Is soapy to touch. Right? So these are the characteristics of base as per the classical definition. So as per the classical definition, a base is defined as a substance whose aqueous solution has bitter taste, neutralizes acid, turns red litmus blue, phenolphthalein pink, methyl orange yellow, and is soapy to touch. Right? Now, acids and base after that have been classified by different scientists, and different scientists had different methodology to classify acids and bases. We are going to see how different scientists have classified acids and bases and how today we define acids and bases. Now let's start with the first scientist, Arrhenius theory. Arrhenius theory of acid and base. Right. According to Arrhenius, this theory was put forward in 1887, and it was put forward not as a theory of acid and base, but it was a part of a theory of ionization. The theory that was propounded by him was theory of ionization, in which he had defined acid and base. That's the brief history. Now let's just see how does he define acid. According to him, any substance which produces hydrogen ion in aqueous solution is acid. Right? How does he define acid? He says that an acid is a substance which produces hydrogen ions in aqueous solution. So any substance that produces hydrogen ions in aqueous solution is acid. How does he define base? In that case, he defines base as a substance that produces hydroxyl ions in aqueous solution. Base is a substance which produces hydroxyl ions in aqueous solution. Right? In that case, how does he define neutralization? According to him, what is neutralization? Neutralization is defined as a reaction between hydrogen ions of the acid and hydroxyl ions of the base to form unionized molecule of water. According to him, how does he define neutralization? It is the reaction between hydrogen ions of an acid with hydroxyl ions of a base to form unionized molecule of water. Right? So do we understand Arrhenius theory? So as per Arrhenius theory, a substance which when dissolved in water and produces hydrogen ions is called as acid. If it produces hydroxyl ions, then it is called as base. And neutralization is a reaction where hydrogen ions from acid react with hydroxyl ions from base to form unionized water. Now, what are the limitations of Arrhenius theory? What are the limitations of Arrhenius theory? Now, if you see his definition, he defines acids and bases in terms of aqueous solution only, not in terms of substances themselves. Right? First limitation is theory defines acids and bases in terms of aqueous solution only, and not in terms of the substances themselves. Right? That's the first drawback. Next, it cannot explain the acidic and basic nature of gaseous substances, because gaseous substances do not dissolve in water. Therefore, the second limitation of this theory was it cannot explain explain the acidic and basic nature of gaseous substances. Right? That's the second drawback of Arrhenius theory. Next, the third drawback, it could not explain the basic nature of some salts which do not contain hydroxyl ions. There are substances which do not There are substances which do not contain hydroxyl ions, and yes, yet they are basic in nature. Arrhenius theory could not explain this, right? Cannot explain basic nature of salts like, say, copper sulfate, ferrous chloride, ferric chloride, aluminium chloride, etc., which do not contain hydroxyl ions, but their aqueous solution is basic. So there were salts which were basic and they did not have hydroxyl ions. The theory fails to explain why, right? Same way, basic nature. Wait, can you just write the salts again? Basic nature of salts like we put potassium carbonate, sodium carbonate, and say amines, right? So it cannot explain the basic nature of salts like potassium carbonate, sodium carbonate, and amines, which do not contain hydroxyl ions, but their aqueous solution is basic. Same way the other way around, it cannot explain the acidic nature of salts like copper sulfate. These are acidic salts: copper sulfate, ferric chloride, aluminium chloride, which do not contain hydrogen ions, but their aqueous solution is acidic, right? Now Arrhenius theory also says that hydrogen ion remains in free state, but in reality hydrogen ion never remains in free state. According to Arrhenius theory, hydrogen ions are always present in free state. But hydrogen ions react with water molecule to form hydronium ions, positively charged hydronium ions, right? Now when hydrogen ions are not present at all, his whole theory is based on the concept that you are going to get free hydrogen ions. When there are no free hydrogen ions, how can I accept his theory? So these were the limitations of the theory, right? Next, let's move on to the next theory. The next theory is Lowry and Brownstein's theory. Now let's see how does Lowry and Brownstein define acid and base. Now, according to them, how do they define acid? According to them, acid is a substance which is capable of giving a proton to another substance, or an acid is a substance which is capable of donating a hydrogen ion to any other substance in any medium. So any substance that can give a proton is called as an acid. Right? Give a proton means, in simple language I could say that accept an electron. So any substance that is capable of accepting an electron would be an acid. Fine. So how does he define? Yeah, you want to ask me? Right? How does he define acid? Acid are substances which are capable of donating proton, which are capable of donating proton, to any other substance irrespective of medium. So any substance that can give a proton would be called as an acid. How does he define base? Exactly the reverse. Substances which are capable of accepting proton are called as, from any other substance, are called as base. So are substances which are capable of accepting proton from any other substance irrespective of the medium. Right? Now, let us try to understand this theory of giving proton and accepting proton. Let us consider a reaction. Example. Let us consider a reaction hydrochloric acid reacts with water to reversibly give you hydronium ions and chloride ions. Right? Now, let's consider hydrochloric acid. Hydrochloric acid is capable of donating a hydrogen. How do I know that? Look at this. You have hydrochloric acid here and the hydrogen is lost when it goes on the product side. That means it has donated a proton. Since it has donated a proton, this is called as acid 1. Okay. Look at hydrogen. It has 2 hydrogens here. Look at water, sorry. Look at water. It has 2 hydrogens here and it has 3 hydrogens here. That means water on the product side is going to accept a proton. Since it is going to accept a proton, this is going to be called as base 2. Let's see from the product side. Chlorine, reversible reaction. If I consider this to be my reactant, chlorine, when it moves on this side, is going to form hydrochloric acid. It is going to accept a proton. Since it is going to accept a proton, we will call this as base 1. Similarly, hydronium is going to lose a hydrogen atom to form water. It is going to lose a proton. Since it is going to lose a proton, we will call this as acid 2. Right, do you get this thing here? So do we understand this reaction? So here you have transfer of proton taking place that results in the formation of acids and bases. Right? Substances which are capable of giving proton are acid. Substances which are capable of accepting proton are base. I'll show you another example. Suppose if I consider hydrochloric acid reacts with ammonia reversibly. No, here you will not have a reversible reaction, right? To give you ammonium ions plus chloride ions, right? Now let's look at hydrochloric acid, guys. Hydrochloric acid, from reactant, when it goes to the product side, it loses a hydrogen. That means this is going to be acid. What it forms is going to be base. Similarly, ammonia is going to, from when it moves from reactant to the product side, it accepts a proton. Therefore, this is going to be base 2, which will give me acid 2. Right? Do you understand this? Now, so this is acid and base as per Lowry and Brownstein's theory. In that case, how do they define neutralization? How do Lowry and Brownstein define neutralization? Now, according to them, neutralization is a reaction which involves donation of a proton from an acid to a base, forming a conjugate acid-base pair. How do they define? I'll explain those terms. First, just let me write the definition. They define neutralization as a reaction which involves the donation of a proton from an acid, donation of proton from an acid to a base, forming conjugate acid base pair. Right? Now, first of all, in order to understand this definition, let us try to understand what is the meaning of the word conjugate acid base pair. Definition of conjugate acid base pair. How do I define this? Now, a conjugate acid base pair is defined as an acid and base which differ from each other only by one proton. So, an acid and a base that differ from each other only by a single proton is called as a conjugate acid base pair. Right? I'll just write the definition and I'll show you the examples of this then. Conjugate acid base pair, an acid and a base which differ from each other, by only one proton, are called conjugate acid base pair. Fine, do we get this thing here? Example, let's consider this. Let's consider hydrochloric acid. Hydrochloric acid, when it forms a proton, it is going to give you hydrogen ion plus chloride ion, right? This is my acid, this is going to be your proton, and this is going to be your, since it has lost a proton, this is called as a conjugate base, because when it accepts one proton, it will form an acid again. Fine. Similarly, let's consider ammonia, NH3, right? When it reacts with a proton, it will form ammonium ions, right? This is your actual base, and this base and this acid differ each other by one proton. Therefore, this will be called as a conjugate acid. This is your proton. So a substance here in both the cases what we see is that the acid and the base differ each other by a single proton or by a single proton, right? That is called as conjugate acid-base pair, right? Now let's come back to the definition of neutralization. In that case, how do I define neutralization? It is a reaction that involves donation of proton from an acid or base to form conjugate acid-base pair. So a reaction in which you have conjugate acid-base pair form, then such a reaction would be called as a neutralization reaction. A reaction in which conjugate acid-base pair is formed would be called as a neutralization reaction. Fine, do we get this thing clear? Now let us consider some more reactions. HCl reacts with water to give you hydronium ions plus chloride ions. We've already done this reaction. Now, in this case, HCl is acid, so we will call this as acid 1, right? It is going to lose a hydrogen to form chloride ions, therefore this is going to be called as base 1. Similarly, water. Here, water is base 2. It is going to accept a hydrogen and form hydronium ions. It is going to accept a proton and form hydronium ions. Therefore, this will be called as acid 2. Right? Now, in this case, which are the conjugate acid-base pairs? In this particular reaction, HCl, here, I can say HCl and Cl minus is one conjugate acid-base pair. Similarly, water and hydronium ions here, this and this are the two conjugate acid-base pairs. Hydrochloric acid and chlorine and water and hydronium are the conjugate acid-base pair. This theory also explains to us the amphoteric nature of water. First of all, what do you understand by an amphoteric compound? What do we understand by an amphoteric compound? A compound which shows both acidic as well as basic properties is known as an amphoteric compound. How do I define an amphoteric compound? A compound which shows both acidic and basic properties is called as an amphoteric compound. Right? Now, here, Lowry and Brownstein's theory explains the amphoteric nature of water. Let us understand the amphoteric nature of water. Let's consider the amphoteric nature of water. Now, according to Lowry and Brownstein's theory, any substance that can donate a proton as acid and any substance that can accept a proton as a base, water is capable of both donating a proton as well as accepting a proton. Right? Now, I can write this according to Lowry and Brownstein's theory. According to Lowry and Brownstein's theory, water can donate a proton and act as an acid, and similarly it can accept a proton and act as a base, right? Hence it is amphoteric. Hence it is amphoteric, right? Example, let's show you the example of water as an acid. Water as acid, right? Let's see example of water as an acid. Suppose water reacts with ammonia. When water reacts with ammonia, it forms ammonium ions plus hydroxyl ions, right? Now, if you look at water here and hydroxyl ions here, water has lost a proton to form hydroxyl ions. It has lost a proton, that means it is capable of donating a proton. That means this is going to be my acid 1 and this is going to be my base 1. Similarly, ammonia has accepted a proton, therefore this is going to be base 2 and acid 2. Here we see that water is behaving like acid, right? Next, let's show you a reaction where water is a base, right? What happens when hydrochloric acid reacts with water? When hydrochloric acid reacts with water, you get hydronium ions plus chloride ions, right? Now if you look at water here, you have 2 hydrogens here, you have 3 hydrogen here. That means water must have accepted a proton. Water must have accepted a proton to form hydronium ion. Since it has accepted a proton, therefore this is going to be base 2. And this is going to be acid 2. And hydrochloric acid has lost a proton, therefore this is going to be acid 1 and base 1. Right? So do we understand this? So from these two reactions we see that here water is capable of both accepting as well as donating a proton, and therefore it can act as an acid as well as base. Fine, do we get this thing here? Next, let's move on to another theory, Lewis's theory. Let's see Lewis's theory of acid and base, right? According to Lewis, what is an acid? Acid is defined as a substance capable of accepting electrons to form coordinate bonds. Sorry, define acid. How does Lewis define acid? He defines acid as a substance which is capable of accepting a pair of electrons, to form a coordinate bond. So any substance that can accept electrons is called as acid. According to him, how does he define acid? Acids are substances which are capable of accepting electrons. Fine, do we get this thing here? Next, how does he define base? He defines base as substances which are capable of donating a pair of electrons. Defines base as substance which is capable of donating a pair of electrons to form a coordinate bond. right? In that case, how does he define neutralization? Right? According to him, neutralization involves acid-base reaction resulting in the formation of coordinate bond. According to him, neutralization involves an acid-base reaction to form, resulting in the formation of a coordinate bond. That's how he defines neutralization. Let's show you an example of neutralization, people. For example, let's consider boron fluoride, right? Reacts with ammonia. Right? Now, boron fluoride will react with ammonia. Here, you have two electrons here which will form a bond to form a complex bond. To form a complex bond, that will be F, B, F, F, and here you would have a bond that would be formed between N, H, H, and H. Right? It is capable of, here in this case what we see is that ammonia is capable of donating a pair of electrons. Since ammonia is donating a pair of electrons, this is that pair of electrons it is donating to form this complex bond. Therefore this will be Lewis base. Since boron fluoride is accepting it, this will be Lewis acid, and this is that coordinate bond that is going to be formed, which will result in neutralization. This is the coordinate complex compound. That's the coordinate bond that I've shown you, right? So here acid and base combine to form a coordinate complex compound, right? So you will have, how do I define this? Here you will have Lewis acid reacting with Lewis base to give you a coordinate complex, right? For example, let's see a couple of more examples like this. For example, hydrogen ion reacts with ammonia. Hydrogen ion reacts with ammonia to form ammonium ion. So what is ammonium ion? Ammonium ion is nothing but, guys, NH3 and H, where, right, you have a bond that is formed this way. In this case, ammonia is giving your pair of electrons, therefore this is going to form your Lewis base, Lewis acid, and that's your coordinate compound. Right? So Lewis acid combines with Lewis base to give you a coordinate complex. Fine, do we get this thing here? So do we understand Lewis's definition of acid and base? Right? Okay, we will stop this here for the day. We will continue with this in the next lecture. Thank you very much.